Well, it's a good thing that the board remains from my previous lecture. And what we'll do is clarify and study more and more details. What we have seen using the old Boyer-Lindquist coordinates, that you have certain surfaces of interest. This is the infinite redshift surface. We talked about why it's called the infinite redshift surface. And there are two places where delta goes to 0, and that's a problem in Boyer-Lindquist coordinates. We called it horizons. We haven't justified it. We will justify it today. And the region, so this region between r plus infinity and r plus is called the outer ergosphere, and similarly you have an inner ergosphere. You have a ring singularity, and then we did a coordinate transformation, and the Kerr-Child coordinate transformation, we call it the k-bar space-time. This is what the metric looks like. In particular, you can see, let me just close the door. In particular, you can see, so everything here is in the bar coordinate system. So you can see dr bar, this is short for, is null. Why can you see that? Well, if you do the inner product of this with itself, it's the r, so t r theta phi. This is the r coordinate. So you can see it's 0. So the inner product of this guy with itself is 0. Let me explain some of our notation. So you have t bar, r bar, theta bar, phi bar. On the other hand, you have t r theta phi. And just by looking at, I had written the transformation matrix, perhaps that, well, you remember it. And if you went through it, you will see that this is in fact true. You can expect certainly this to be true. What is not true is the fact that dr is equal to dr bar. This is not true. I think we may have even worked out last time what it was. I don't particularly, yeah. So as a matter of fact, where's the eraser? dr, using the transformation matrix we wrote last time, it is r squared plus a squared over delta dt plus dr bar. Dr, so this is unbarred, everything here is barred, plus a over delta d phi bar. So whenever I write, so r, theta, and well, r and theta, they're exactly the same in two coordinate system as functions, but they are not as vector fields, meaning r bar equals r, theta bar equals theta. Okay? There is no need to distinguish theta coordinates at all, because theta bar equals theta, and partial of theta is equal to partial of theta bar, and you can easily check that d theta bar is equal to d theta. So when I write either Boyer-Lindquist coordinates or the Kerr-Child coordinates, I don't need to put a bar on theta. You just can't go wrong. I don't need to put, in terms of coordinate functions, I won't write r bar all the time. I'll just write r because r equals r bar. But when I'm writing the vector fields, I need to clarify, do I mean ddr or ddr bar? So only in forms and vector fields we will make the, we'll make it clear. Okay, so I could use this for a while, but I don't need this.
Y informs, I think it's just vector fields, right?
So dt bar is not the same as dt.
Well, let's talk about r and theta.
Right. R and theta, it is the same, but I still, you're right. I don't need to clarify. It's only in vector fields that I need to clarify. Yeah. But whenever there's a confusion, I'll clarify. We're going to talk about causality today, so I just want to use an acronym that is not really used anywhere, but I don't want to write letters all the time, so I will use, wait for this, FPT to mean what? Future pointing time-like. If I use FPN, I will mean future pointing null. PPN would be past pointing null, and PPT would be past pointing time-like. Okay, so we're going to talk about causality, and we're going to penetrate. We stopped at the infinite redshift surface yesterday. We're going to slowly come in. Okay? Well, I might need this for before. I don't need anything else, I think. Okay, where are we? Yeah. So this is, by the way, this is infinitely far away. So right about here, right? So far away from r equals 0. We would want this ddt to be future pointing time-like. Correct? We know that minus dd bar is null. I'd like to know if it is, well, we know dd bar is null, so minus dd bar is also null. I would like to know which way is minus dd bar pointing. And because that will give us an incredible advantage in studying the ergosphere and perhaps the black hole region. We haven't mentioned it. We've talked about two horizons. We haven't clarified all of that. So the question is, what is it? So what I'm going to do is infinitely far away, I'm going to take the inner product of right? So, well, this is the same as g of dt bar minus dr bar. I conveniently erased the metric. This is minus g t bar r bar, which is what? If you looked at the t bar r bar term, it's 1. So this is minus 1. So if you have a null vector whose inner product with the future pointing time-like vector is negative, what can you conclude? It is future pointing. Therefore, minus ddr bar is future pointing null. We talked about this last time. One way to realize if a vector is future pointing, you take an inner product with another future pointing vector, and if the inner product is negative, you have a future pointing vector. Good news is the metric is not singular over the horizons. Furthermore, this is a future pointing vector everywhere outside, everywhere far away. But this vector is defined everywhere. Therefore, this is going to distinguish our future light cone. Any causal vector that is in the same light cone as this one is future pointing. Correct? Very, very quickly.
What does it mean to be in the light cone again?
So we talked about this, but nonetheless, very quickly. See, if you take let me take, yeah. So if I take a light-like vector that's on the light cone and call this, let me call this L1, and perhaps another one, let me call this L2, and let me call this something, let me call this T for time-like. If they're, you can see visually that they're on the same light cone. It's pointing this way, they're all in the same cone as opposed to this one. You can be assured that the only way this happens is if and even the only way two vectors in the same light cone can be 0 is if it's a null vector. I mean, obviously, it's a light-like, L for light-like, sorry, L for light-like, T for time-like. As I have probably drawn, you can tell. L lies in the boundary of the light cone. Yeah? Is that clear, everyone? That is how you pick out your future. So by declaring this to be future pointing null, I have now given a time orientation for the space-time k-bar. Time orientation or light orientation, light cone orientation. So let me make that very clear. This fixes the future cone everywhere in k-bar, sorry. So if I want to know if a causal vector is future pointing, I take its inner product with this guy. If it's negative, it is future pointing. If it's positive, it's past pointing. Again, you can take simple, if this is confusing to you, you take simple examples. You can pick T to be 1, this is in Minkowski coordinates. -1. Yeah? Sorry, same light cones, this way. And you'll see these rules follow. Any vector and time-like vector by a Lorentz transformation can be put into this category. So my rules will apply. Is that clear? Okay. We have fixed time orientation. We're ready to. By the way, I just need the space, so I'm going to remove this and put it back in later as needed. So this is my conclusion 1 for the day. Some of these are just obvious points. 2, kind of interesting feature, dt dr. No, I didn't put bars. I think it's true for bars as well. It is, yeah, d4. They're all space-like in the ergosphere. Why is that? Well, this is the surface, GTT is equal to 0. GTT is negative, infinitely far away, like Minkowski spacetime. Here GTT is 0, so here GTT is? From negative you come to 0, then what are you going to go to positive? So that too becomes, so it's a curious, there's nothing miraculous about it. Again, just because you see T doesn't mean it's time-like. I just want to point that out. So you have a basis vectors, all of which is space-like. A neat feature. And I'll always point out this neat feature that will teach you about global, sort of not, if not global, just Lorentzian geometry in general, just features, and also a little bit of GR, because the more practice you have, the better it is. Okay, the third point is, and you might wonder why I'm doing this, this is for something that is coming up very shortly, in the ergosphere. You can see the advantage of my notation here. In the ergosphere, gradient of t is past pointing time-like. First of all, let me show you that it's time-like. Or, well, sure. This, we didn't write the inverse matrix or inverse metric. If you did, this GTT would continue to be negative, right? So it is time-like. Remember, GTT lower in the ergosphere is greater than 0. Okay, please verify that. If that's, I'm sure that's true, but if that's not, we need to check, huh? I may not have written the inverse transformation, but we'll check and clarify that is indeed the case. But I have shown that only gradient of t is time-like. I've not shown that it's past pointing time-like. So let me ask you this. How can I show it's past pointing? I have to show that, yeah, precisely. This better be less than 0, because this is future pointing, right? But I'm going to cheat. This is the Boyer-Lindquist t coordinate. So what I'm going to do, remember this is the infalling null geodesic, correct? So this is r squared plus a squared over delta t minus dr plus a over delta d phi. So then I have g, this is really n mu. Correct? So this is g mu nu n mu nu t, or this is equal to n mu correct? And that's equal to n0, which is r squared plus a squared over delta. We're still, this is the ergosphere, this is not inside the horizon, this is greater than 0. So this guy is past pointing time-like. Any questions? Because the next calculation I'll do is important. Yeah? Okay, so this is the result we have, and I'll hang on to that. So T is not time-like in the ergosphere. So then the question is, in the ergosphere, can a causal particle not move in time? Again, interesting feature. Even though T is not time-like, a causal particle has to move in time. So let me set up a notation. If you have a 4 velocity of a particle, you would have T, you can write it as T dot R dot theta dot phi dot, right? Where the derivative is with respect to its proper time. And of course, if it's causal, u squared is less than or equal to 0. Equal to 0 meaning it's a null particle. Okay, so here's my claim. And that's 0.4. In the ergosphere, T dot is greater than 0 for a causal particle. Well, that's easy. What I'm going to do is G mu nu, U mu. This is the reason I introduced that vector, the gradient of T vector. Once again, this is equal to U mu. Yep. So now, this we know is future pointing causal. This we know is past pointing time-like. If I take a future pointing causal vector and a past pointing vector, their inner product will be what? The opposite of when they're in the same cone. When they're in the same time cone, their inner product is negative. So, if they're in the opposite opposite time cone, the inner product must be greater than 0. What is this saying? This is, again, only the 0th coordinate. And what does that mean? A lot of analysis is made simpler just talking about something in geometric terms. And there's a lot about general properties of black holes we can learn. We'll talk about the geometry of the horizon in particular. And then you'll see why many of the results in causal theory of the horizons has to be true, just intuitively. Just in a story or in a song it can be explained. Yeah? Okay. I've been rushing through these sort of calculations. I just wrote that as GTT. Most of you may know it, some of you may not. Let me clarify. And I did that here too. And I've done that in the past. This is nothing partial derivative with respect to T r theta phi of T. Well, the only way the partial derivative is not 0 if this is T coordinate or the 0th coordinate when mu is 0. And that's why u0 remains. Same thing over here, huh? So what I'm trying to say is d mu of t is dt of t dr d theta d phi. Oh, sorry. Obviously, this is 1, 0, 0, 0. So only the 0th component exists, and that is why this became G00 or GTT. And same thing over here. This became U0, t greater than 0. Fine. We're cruising along. Any questions? Okay, anything I should clarify? Point number 5. Let's call this frame dragging, huh? Again, we get all this results for free. In the ergosphere, phi dot is greater than 0 for a causal particle. That's easy. I'm going to do u squared, and u squared is g t t t dot squared plus g phi 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 dot squared plus 2 g t phi t dot phi dot. There's more. Well, I could g r r r dot squared plus g theta 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 dot squared. Has to be less than or equal to 0. And just by a quick inspection, you can see that these guys are positive. Only way this can be less than or equal to 0 is if g t phi t dot, this is t dot, phi dot is less than 0. Yeah? GT phi is negative. This is a negative quantity. T dot is a positive quantity. So the only way this can happen is what? So again, interesting feature, ergosphere, ddt, ddr, dt theta, dt phi, they're all space-like. Nonetheless, for a causal particle in the ergosphere, t dot has to be greater than 0, and phi dot has to be greater than 0. They're space-like quantities, and yet they have to be greater than 0. And this particular effect, what it's saying is, including a beam of light, as it falls into the region of the ergosphere, it has to start rotating. Yeah? With the black hole, if you will. So this is what is called frame dragging. Everything causal is being dragged in the phi direction. It is sort of rotating with the hole. Sort of a nice result we get for free. So yeah, these are all positive. Well, the most important point, why is this positive? It's easy to quickly write it. Again, we are in the ergosphere. GTT is positive. Yeah, that's what makes this interesting. I'm just cruising along. Any questions? Anything we should discuss? Yeah.
What's the meaning of T dot positive?
Well, I mean, it simply means really we cannot attach much meaning to it. It just means that the T dot coordinate must be increasing for a causal particle, even though T is not a time-like coordinate in the ergosphere. So there are other ways, and I'll show you why. A picture is worth 1,000 words, and I often tend to conclude with 1,000 words. Yeah. Okay, so now let's fall in. Remember, I call this outer region block 3, and this is block 2. So we have penetrated the ergosphere. We've talked about the geometry. There are other exotic properties we'll talk about. In particular, we might get to talk about energy extraction from a black hole, the famous Penrose process. But that's not our job today. We're studying just causal structure. Yeah. So, in block 2, so we have left the ergosphere, so I think I've restarted my labeling. If I look at this guy, not R bar, but R. First of all, what is this guy? Well, the minus and minus cancels. This is rho squared over delta. But we have reached block 2. These two boundaries are defined by delta equal to 0. Here delta is greater than 0, so you can imagine what delta is over here. So this is less than 0. Okay? Now I want to know what, well, that means it's time-like. So then I want to know, well, which way is it pointing? Well, so I take my infalling geodesic, which I have designed shown in fact to be consistent with infinitely far away, that is in fact future pointing. This is minus from here. This has a r coordinate which is 1, so G R R, and this is infalling minus 1. So this minus comes from here. N is infalling geodesic, it has a minus 1. And so that is G R R, which is what? Again, rho squared over delta, which is less than 0. Therefore, minus DRR is future pointing what? Time-like in block 2. So this is my future, if you will. The negative r hat direction, or negative DDR, where r is decreasing, that is my future. So you've taken a course in relativity, you've seen short shield geometry, and this is precisely the reason why we might call it a black hole region. It's a one-way membrane. The decreasing values of r is future pointing. Yep, for a time-like. So anything that falls into it, its radius, not radius, its r coordinate has to decrease in region 2. Well, let's show that. So again, u is a 4 velocity of a causal. So that is minus, this is r, this is Boyer-Lindquist coordinate system, r dot, and then GRR, rho squared over delta. This has to be, if this is future pointing, this has to be less than 0. This is less than 0, this is less than 0, correct? This is less than 0, this is less than 0. So the only way you can get this to be less than 0 is if r dot is also less than 0. So this is why Kerr black holes, whatever black holes are, describes black hole space-time. There's a one-way ticket. So if you somehow manage, if a causal particle somehow manages to enter into block 2, its radial coordinate, its r coordinate keeps decreasing. So it's a one-way membrane. You just go in. Once you're inside, you have to come out. Yeah, we'll talk about the horizon itself. Yeah? Good. These are all easy to prove, but these are all important facts to sort of remember. That is why I'm just sort of listing it out. So a little bit of homework. You know, we have the infalling geodesic and the outgoing geodesic. Remember, what was the outgoing geodesic? Well, it's exactly like the infalling geodesic, but what's the only difference? Plus dr. Well, we know this is a null geodesic. But what happens if you are in the black hole? Can it go to increasing values of R? So a quick check will verify, because we have the tools for it, minus L is future pointing null in block 2. So when you have minus L, you would have minus DDR. So even the outgoing beam of light is trapped by this black hole region, and the outgoing light also falls inward. Yeah? So you will see an interesting feature shortly. This outgoing geodesic, if it just touches the geodesic and you start an outgoing geodesic, it's going to stay on the horizon. But if you cross it, it too falls over. The light cone will tip over. Again, a reasonable diagram would clarify that intuitively. Okay. So I think that's all about block 2. I want to talk about the horizon itself. I want to talk about the geometry of horizon itself. How are we doing on time? I've just been going
35 minutes in.
Okay, so let me get started then. So these are given by R equals R plus or R minus. We've been calling it horizons. Now we sort of know why, because it's the boundary of this black hole region. And sometimes I might even refer to the surface, the surface defined by R equals R plus and R equals R minus as H plus and H minus. Well, you know why? Because they are the horizons. Now we have context for this. So to talk about the geometry of horizons, I want to do the following. I want to look at L. I'm going to approach the horizon from the outside. Why from the outside? I can start off with the Boyer-Lindquist coordinates where everything behaved nicely, and then I'm going to slowly approach. I'm going to look at this guy plus DDR and no. Well, I said I'm going to slowly approach. I don't mean that. What I mean is I'm going to convert this to Kerr's child coordinate system because I'm going to get to the boundary. Okay, so first what I'm going to do is write this in Kerr's child coordinate system. I know this guy already. It's R squared plus A squared over delta because ddt is the same. And I'm going to bring this over here too, because that is also, oh, sorry, T bar. In the beginning, I had written down partial R in terms of the Boyer-Lindquist. And I think it is exactly r squared plus a squared over delta dt plus dr plus a over dt bar. As a result, this is 2 r squared plus a squared over delta dt bar plus dr bar plus a over delta 2. We know that this is a null geodesic in Kerr's child coordinate system. I'm not going to give this a name, but because we will eventually. I'm going to look at this vector. You can see why. And I get this to be r squared plus a squared ddt plus delta over 2 dt bar plus delta. What is this vector? This vector is a null vector that is proportional to the what? Null geodesic. Yeah? The reason being, and you can see why I multiplied by delta, because I want to get rid of this delta. And then I'm going to do this. I'm going to take the covariant derivative of this with respect to this. So I need to be careful about nablas and delta, so please keep me in track. Well, I can bring this guy out, and then I have L acting on delta over 2 and times L plus delta squared over 4 delta L delta. Correct? Well, L is a null geodesic. I can get this out of the way. So this is delta over 4. Delta is only a function of r, so I would have ddr of r squared plus a squared minus 2mr times L, and that is delta over 4 times 2r minus m times L. Let me write down what I mean to write down at the end. This is all in Kerr's child coordinate system because everything is t bar, r bar, phi bar, so on and so forth. So what I've shown is I could do this. What does that mean? That delta over 2L is a null what? Pre-geodesic. And I will pose a question and maybe even discuss it next time. What is a pre-geodesic? It can be reparameterized to read to have 0 on this side. So you may or may not have seen this in your GR course, but today we're going to, so let me be very careful. Let me explain. If, suppose you have a vector u equals 0. That's a geodesic equation. But suppose you have covariant derivative of u with respect to u is proportional to some function n times u, function of the parameter of the curve. Then this is a pre-geodesic. What that means is you can change your parameterization and you can get this to be 0. We'll just take that for granted because we are also learning geometry along the way. And maybe if I'm patient enough, I'll find out what that factor is and next time and show you the explicit calculation. But really, it'll be good practice for you to show that this can be reparameterized to look like a geodesic. Okay, so then what I'm going to do is the following. I'm going to take this guy, which is this, and let delta go to 0 and evaluate this vector field at the horizon. So then v plus minus, I'll clarify the plus minus, it's not what you're thinking, is equal to, well, let me write this. I'll put the plus minus. So if you wrote it, don't erase it. But let me organically grow it here. dt bar a d phi bar is a null pre-geodesic vector field at the horizon. What did I do? Over here, I let delta go to 0. At the horizon, because this is smooth. This is Kerr-Child coordinate system. Yeah. So let me make that very clear. Now, by plus and minus, I mean on the outer horizon and the inner horizon, which means R has to be evaluated. Oh, not the. Then is a null pre-geodesic on the horizon. Actually, I should say everywhere except poles. You only learn when you do some of the boring insightful calculations on your own. So let me just state this. Which way does the pole rotate? If you have a spinning ball and if you have an axis, at the poles, we'll take V plus and minus to be d phi just goes to 0. We'll also do a coordinate transformation where we remove the singularity at the poles, meaning a coordinate system that is valid along the poles. And you'll in fact see that d phi is not well defined on the poles. The spherical coordinate system is not well defined on the poles. And d phi does indeed go to 0. So on the horizon, on the outer horizon, there's a null geodesic vector field. On the inner horizon, there's another null geodesic vector field. So at h plus and minus. So this is defined by r plus minus equals a constant. What vector fields span this submanifold? Well, r is a constant, so dt bar, d theta bar, d phi bar span the horizon. Notice this guy is contained in the span of this. And we'll talk about, I don't think I have time for it today, but we'll talk about the nature of this submanifold, some of the geometric properties of the submanifold, and
How do you know the horizon is a submanifold?
it's defined by one of the coordinate functions equals constant. If dr is not equal to 0, and it's not, then the resulting space is a submanifold. It's necessarily so. Well, it's a slice, so we have an adapted coordinate system. Again, I'm using words that typically is not discussed in a freshman GR course. But it's a three-dimensional object. It is spanned by t, theta, and phi. So it's a three-dimensional submanifold. We'll see, and we will see, that it is not a semi-Riemannian submanifold. We'll see that the metric is in fact degenerate. But let me draw a diagram. We know that the horizon contains a null vector. I know how to draw null vectors, so I know how to draw a horizon. Null vectors go at 45 degrees. So, and then I'm going to draw a light cone. Remember? Let's say V plus. It has a t component and it has a phi component. So this is a null surface. It's the cone. But it has a phi component, so to clarify that, I will show, it is clear that V plus looks like this. It has a phi component. I'm just saying it has a phi component. This is also V plus. It's the V plus to a point slightly over here. That's all. And what is this guy? The infalling null geodesic. Vector field. Oh, you can make it this too. This is also V plus. So the horizon consists of one light-like vector field and two more vector fields in here to span it. We can write it as t bar, theta bar, phi bar, but it's better to, we will see it's better to use two other choices. And in fact, it'll be made clear how the metric becomes degenerate. Okay? But the horizon, so a lot of physics, a lot of clever theorems can be understood in simple terms. One is a very important fact that a horizon consists of a null vector field. If it's a horizon, things are tipping over. Perhaps another drawing is important. If we were to consider r as a radial distance, or radial coordinate, maybe I could have drawn it like this. This is r equals r plus, and now my light cone would look like this. And this would be my v plus, and this will be minus d. We know this is an infalling null vector field. So the light cone is just beginning to tip over. If it's going to tip over, horizon is the boundary. It must consist of a light-like vector. Furthermore, this and then it would consist of, it's a boundary. There's no other particles that can exist to it. The other vector fields must be space-like. Now, there's a result. It's simple calculation. You can show that if you have a null vector field, a null congruence in a null surface where the metric is degenerate, this vector field has to be what? A geodesic. You can have fancy geometry to show that. It's not very difficult to prove. But nonetheless, if this weren't a geodesic, you could have a time-like vector catching up with it. well, then it wouldn't be a boundary. In the boundary, only a light-like vector can exist. And you know, if it's not a null geodesic, it can be varied slightly to produce a time-like vector. So any vector field in a null hypersurface has to be a geodesic vector field. And it is necessarily, it has to be a three-dimensional hypersurface. You can have, and why wouldn't I mention this? For example, in force-free electrodynamics, you will have two-dimensional submanifolds that is light-like. And you will have a null vector. There are degenerate, this is called actually null solutions of force-free electrodynamics. You would have a two-dimensional subspace, which is degenerate, which contains a light-like vector field. It doesn't have to be a geodesic vector field. Turns out, just miraculously turns out, the force-free condition requires it to be a geodesic vector field. Yeah, so there's lots of interesting feature there. So there's a larger geometric point to be taken here. If you have a null surface, a null hypersurface, we'll spend a little more time talking about the horizon. If you have a null hypersurface, the null vector field has to be a geodesic or a pre-geodesic. Otherwise, a light-like vector can catch up with it. And you cannot have a time-like vector can catch up with it. And you cannot have a time-like vector field in a light-like hypersurface. We'll also see that all the vector fields that are perpendicular to a light-like vector field is a light-like vector field or two other space-like vector fields.